So welcome. Our third lecture today, we will look more into the different concepts that are implemented. But before I do this, I would like to quickly go through the missing slides of the last lecture, which were about the contemporary history. And I pointed out these three phases here. The first decade of the century with the pioneering developments, then the second phase, the second decade, where the development got more and more networked internationally, and then the third phase since about 2020 with the first commercial prototypes in operation. And I showed already this timeline where you see here the first decade with the pioneers. Then you see from 2010 onwards, really a rather large involvement, between 40 and 60 companies and universities involved, and that number has even increased now. One of the early players was Makani. Makani is a US based startup from 2006, and they first experimented also with surf kites. Here you see such a classic sea kite. They flew on Maui, on an island in Hawaii. Here you see the nighttime operation. And already in 2007 they had automated the flight in crosswind maneuvers. You see that here with long duration photo and light. And what you nicely see here from 2008, you see the multi-winch setup. This is the kite, and here you see the power line, one line and two control lines that are actuated, and you see that they were in long-term operation with the kite. And this is just also again for historical interest. This is Miles Lloyd here on the right hand side, basically the engineer from California who in the 80s presented the first theory on crosswind kites. And on the left here, Damon Vanderlind, who was then the chief technology officer of Makani. They then went they transitioned towards fixed wings because they already early on realized that these soft wings are not very durable, and they had the idea, okay, if we go to fixed wing, we solve the material issue, and at the same time the automation will be simpler, because to launch such a kite and land such a kite automatically, you see it actually here, is quite complicated. This is still one of the continuing challenges for our field. So they made the decision, we go fixed wing, and that solves several problems. And with fixed wing, they also decided to go for onboard generation. You see here 4 onboard wind turbines that they could also use in propeller mode, and use this entire aircraft as a so-called tail-sitter drone. Tail-sitter means it launches and lands from sitting on its tail, and in this case it was not sitting; it was hanging on a launch mast. But that's still the same. We will see photos about that. What you nicely see also here is this is not a conventional drone, so the rotors are quite over-dimensioned because they are also used for harvesting the wind energy. Here you see the tailplane with the rudder and the elevator. Then in Delft we had Wubbe Ockels, former Dutch astronaut, was in space in 1985 with the Space Shuttle Challenger, and he was the one here in Delft to launch Airborne Wind, and that happened about even before 2000. He had a first patent on on a so-called ladder mill, which is a large, I'm not sure if I have a slide, which is a large cable loop into the sky with several kites attached, which could go around. And that patent is from 1998. We later went towards a more simpler setup, which you will see later in the next lecture. This is more or less a chronological step through. In 2010, we had our first Airborne Wind Energy conference. Actually, it was the second. First one was in Chico, California. That's the second one in Stanford. And that was already quite large. I think we had about 100 to 150 participants. There was a very, let's say, visionary and pioneering spirit. It was a time, 2010, when there was quite some investment money available, especially in the US. And you could see that the US-based airborne wind companies really flourished from that. 2011 conference went to Leuven in Belgium, then in Berlin in 2013. You see that this crowd is more and more increasing in size. Here we were already 160, 70 people. In Delft, 2015, organized by me. You see our campus. Then Freiburg, South Germany, was a strong center for control research on airborne wind. Then in Glasgow, 2019, in Milan, 22, and then I think there was also the textbook, the Springer book, which you will see in the references. You see that we had, it was quite, I think it's quite a well-read book. It had 150 accesses in October 23, which is quite good. Then another textbook in 2018. Together, I should say, more than 1,000 pages of condensed theory, which we still use as a major body of knowledge nowadays. We had a journal special issue in last year with 23 published articles. We also have this IEA task 48. You will probably hear about this throughout the lectures with work package on different subjects. These 5 subjects are all of importance for airborne wind, where we try to cluster resources. Several companies and universities work together on these topics to use synergies. It's following the motto, together we are stronger. Of course, that works also here. 2021, we even made it with kite power on a Dutch stamp. It was a so-called TU Delft Innovation Stamp that was issued by PostNL. And this is the airborne wind energy scene as it is now. You see that most of the activities are in North America and in Europe. We do have some here in Japan, also in China. But I would say the difference between the US and Europe, you have to follow these lines here. The difference is that in Europe, I think we have a better academic industrial network, and that comes through the fact that there was quite some research funding also issued by the European Commission and by the national funding agencies that really created a well-balanced mix of companies and universities and governmental organizations to conduct network research. In the US, it was mostly private investment that went into companies, and Makani was one of the big, let's say, investment objects. Good. That was so much about the historical development. Then I'll just head over to a nice continuation. Let me see. And that is my presentation on the implemented concepts. In this lecture I want to show mostly what's been done now and maybe a few highlights that were so important that are not continued now, but they are so important that they are worth mentioning. This is my outline for today, and please interrupt me if you have questions. We will really look in detail at some of the concepts, and I'm not sure if everything is clear. The first thing what we'll do is we discuss a few classification options. So airborne wind is still a technology that sees many different concepts. There is no clear winning concept. You see all different variants, and it's often hard to orient yourself in this, I call it zoo. So first let's give it a shot how to classify things, and then we look at the different concepts one by one. Learning objectives, basically what I just said, in essence classification, and then look in detail at the individual projects. And for classification, the first thing that we can do is we can look at how the energy is converted. Are we converting at the ground or in the air, or in another way? I have some examples on this in future slides. Then the kite design also plays a role. The launching and landing concepts, how do we control the kite? And you could also classify according to the rated power, so small, medium and larger size system. But what we see is that the classification criteria are of course also correlated. So once we decide for an energy conversion concept, there is often a strong choice for a specific kite design, or how to launch and land the kite. They are interrelated, right? Give you an example. If you want to have onboard generation with small wind turbines on board of the kite, it doesn't really make sense to use a soft wing, obviously, because where do you attach these turbines? The soft wing is a tensile membrane structure which doesn't have hard parts. So it's difficult to attach wind turbines here. Second, for onboard generation, you want a very fast flying kite so that the turbines see high incoming airflow. But these soft kites are not the best ones for high flight speeds. So for onboard generation, you really want to go towards a fixed hard wing concept with high lift to drag ratio. And you see this coming back by the fact that this let's say soft wing and onboard is simply not implemented. Okay, so let's look at this first criterion, energy conversion concepts, and this is something that you have already seen. I showed this in earlier lectures. You have the ground generation concepts, where the conversion of mechanical to electrical energy happens on the ground, and you can have either a soft wing that actually pulls the tether, or a hard wing, and we have a reel out and a reel in phase, but technically both do the same, only the kite here is different. And then you have the onboard generation, where the turbines are on the kite and the electricity is conducted down. The winch is only used for launching and landing to reel out and reel in the tether, but it's not used for electricity generation. And you see that there is no soft wing with flight gen here in this concept sketch. And then we have this third class, or fourth class if you want, where you have a rotational kite. So the entire kite rotates. It's basically a flying wind turbine rotor, and that rotor drives a networked tensile axis, you could say. These elements here are rigid, and they make sure that the tethers stay in place, but this whole tensile construction actually rotates and it drives the generator here on the ground. And this kite up here has the function to provide additional lift to get this whole array of this rotating chain into the air. Then, are there any questions regarding this here? Everything clear? Then we move on to the second criterion that I mentioned, the kite design. And that's pretty straightforward. It can be a hard wing kite. I call it hard wing because I heard that fixed wing is often used in relation to helicopters. So we are still searching for the right terminology. Then we have the soft wing on the other end of the spectrum, where everything is membrane, and we have these tethers and the bridle system. And in between this hybrid kite, the hybrid kite, in this example, this is the inner kite wing, you have carbon fiber spars, and the canopy itself is a textile that is forming the aerodynamic surface, and it's treated with chemicals to put it under tension. You have to imagine this like you would build a model airplane, or the airplanes that were built around the First World War. It's the same construction principle, only we use modern materials. And in practice, you will find many variants of kites here in between. Also the soft wings kites, they use rigid stiffeners to have increased wing loadings. Okay, and what you see here nicely is that the control concept is also correlated with the type of kite. Here we have aerodynamic control surfaces, while here we use the tether, the bridle line system to actuate the wing, and here the entire kite is actually actuated by the two steering lines. Then the launching and landing concept. So here we have this tail sitter drone, and VTOL means horizontal. Sorry, I mixed this up, I just see. VTOL means vertical takeoff and landing. HTOL is horizontal takeoff and landing, of course. So here you see that this drone sits basically on the tail, lifts off vertically for launching and landing, while in this concept we have a horizontal takeoff and landing from a catapult. So the catapult injects kinetic energy into the aircraft so it can lift off. It's tethered, so there you can already imagine here that there will be a transition phase where you go from launch, where the tether is slack and just fed out, into a phase where the kite flies crosswind maneuvers and the tether is highly tensioned. And you can already imagine that the transition from the one mode, takeoff, to energy production is critical. That is when the tether goes from slack to fully tensioned. The load on the aircraft increases dramatically, and that's normally when things could go wrong. So that is a very critical phase. Landing is similar. You need to basically go on the return path and land on a very small platform. And then you have this horizontal takeoff and landing with a rotating arm. That's again the inner kite wing, where you use a rotating arm to catapult, you can also say, the wing into the air. So there is a similarity between these two concepts in the sense that kinetic energy is injected into the wing before it starts flying. Yes?
If you've got really strong wind, can you still do the rotating thing?
Yeah, that's a very good question. So this platform normally can nicely rotate into the wind. You can actually launch against the wind or with the wind if your catapult is strong. With this you don't have this option, and from what I know, it is possible, but the control of the kite while it goes through the different incoming wind speeds is quite tricky. You can compare this a little bit with the vertical axis wind turbine, only with the idea to at some point let go of the blade and bring it into free flight. So the launch here has the same complications as a vertical axis wind turbine in operation. And you can imagine with a vertical axis wind turbine, you have a constantly unsteady flow condition, because the blade at every moment along its rotation sees a different inflow velocity. So this is tricky. They managed to launch and land this year for the first time in this setup, and I have a video about that. Then we put this scheme together, and this is one option that you could think of. When we, let's say here we start with the basic system, then we differentiate according to the electricity generation with fixed ground station on the ground, a moving ground station on the ground, I have not mentioned this yet, or energy generation on the flying device. And then we split off further into crosswind or no crosswind or rotational. I want to basically, so this is fly gen, ground gen, I want to basically go through these tracks. So these three concept lines are the ones that I showed in the earlier criterion 1 slide, if you remember. What's also very obvious is that this track here, fixed ground station, flying crosswind, has all these companies, which is a dominant number. So most of the companies actually follow this concept. Then you have here on the flying device crosswind, we have 2 companies that currently pursue that. Makani was one of the originally 3, but they stopped operation. And then we have the rotational kite with 2 concepts. We will look at most of these concepts today. What I put here into this legend is other classification options according to the kite type. So you see that half of the concepts here are with soft wings and the other half is with fixed wings. We have also lighter than air concepts, that's here wind fisher, and there is one concept, kite swarms, that also uses multiple drones, so not just one kite but multiple ones. Is this more or less clear, this diagram? This is a bit a guiding scheme for what we will now see in detail. And what will we see now in detail? These are the currently developed 14 prototype systems. These are all companies, all small, except SkyCells is quite large. They have more than 50 people under contract. Kitebauer and most of the other companies here, about 10 to 20 people, and also some 2-3 people startups here. So here you see the soft wing concepts, until here, So these first 4 typical soft wing kites. Then we have CPECC, which is Chinese, in operation since 2010 already. They use large parachutes to pull the tether off a drum with a pilot balloon or pilot parachute here. So this is a bit of a special concept. Then wind fisher, Magnus cylinder. So this is a rotating cylinder that creates lift. I mentioned this in one of the earlier lectures. And then Enerkite, Zairo, and all up to here, they are all fixed wing or hard wing drones. The last 2 here with with VTOL rotors, in this case 4, in case of TwinTech 3. Mosa Aero is simply a large flying aircraft with auxiliary propellers here for launch and landing. Kite does not have any onboard propulsion. It's the most lightweight kite system. And then here you have the current 2 onboard generation systems. Okay, let's start. I will go from left here to top to right down. I have not been able to put all concepts in here so far, but yeah, let's see. So SkySail's power, they are active since 2001. SkySails is probably the oldest company that's out there. They are based in Hamburg, Germany. They envision, or they follow the pumping cycle concept. They have a ram air wing that they use. They use a suspended control unit flown with a single tether, and their launching and landing is a static mast setup. What is notable that in 2001 SkySail started with pulling ships with kites, large kites. So they built kites of 300 to 600 square meter surface area, which are quite big. But the market for ship propulsion was apparently not a good market, not a market that was easily awaiting a new concept. In 2016, SkySails went bankrupt, although they had a technically quite well worked out solution. So they went bankrupt and they relaunched with energy generation in mind. And luckily they were able to safeguard most of their engineers and put them into a new company, SkySail's Power. And SkySail's Power then has become the world leader of airborne wind at this moment, without any doubt. They use a control unit and a specific steering concept that I show here. So this is the wing, that's the control unit. Here they have in the control unit mini winch that can roll the entire wing, which you see here. And by rolling, they rotate the aerodynamic lift vector either to the left or the right. They fly like a conventional aircraft. They can roll the kite and then fly a turning maneuver by this. We will look at the physics of these kind of maneuvers in later lectures. But just to give you a conceptual idea. So what SkySails also can do is, since a year or 1.5, they can pitch rotate the entire wing. So they can not only roll it, but they can also change the pitch. For this they use a second mini winch within the control unit. Okay, and this is how launch and landing works. So you see that the kite is deflated. It has these openings here, which are, when faced into the wind, deploy the kite or inflate the kite. And the kite, here's the control unit, then can take off. You see there is I was a bit too quick. There is a fifth line, we call it, attached to the leading edge, which allows the kite to be pulled towards the launch tower. And when you watch these videos carefully, you see this fifth line actually been dragged around. It's in addition to the main tether. This is here in northern Germany, where they have one of their test sites. And then they go into power generation mode. You see this here from drone view. And they fly also up to 500 meters, although the altitude is not really any limitation. Okay, what's nice? So this kite, just to give you an idea, it looks small here, but it's 180 meter squared. You see here the fifth line and how it pulls the kite towards the launch mast. That is required so that you can decouple and couple back the kite to this mast. And we are using this fifth line also with kite power, and I will show you later, but not for mast-based launching, but as a safety mechanism when the main tether breaks, which it shouldn't. Okay. Are there any questions regarding SkySails before I continue? No, everything's clear. Then let me move on. I put kite power together with TU Delft. Let's start first with TU Delft. Of course, we know most about this because we developed this ourselves, so I can go a bit more into detail. Basically, we started in 2004 here in Delft as a research group. So we were not, we had of course commercial aspirations, but we were not operating commercially with the leading edge inflatable tube for pumping cycles with the suspended kite control unit, which I brought here, single tether, and we operated with classic winch launch, so positioning the kite downwind on its tail and then use the winch to launch the kite up, or from a launch mast in a swinging configuration. Okay, so that is the setup that we use. Here our ground station 1, we call it, because now there are more. The kite itself here, that's 3D print of this kite, 25 square meter. The kite control unit, you see here, it's this box, we'll open it later. The control unit communicates wirelessly with the ground control center. We have also a wind meter, which is also connected, and this is the launch mast, which is an add-on for experimentation. Okay, here I put all the elements. The tether itself, what is notable, what I forgot to say, the battery module was really integrated here with the ground station, so it could be a self-sufficient off-grid operating kite system. And that is something that I already explained, the working principles, so we don't need to go again into this. What we already built in very early, before SkySails to our knowledge, is the capability to depower the wing with this kite control unit, meaning we could pitch the entire wing down by reeling out the two rear steering lines, or the two steering lines, and this way the kite would tilt. You will see this later. This is a simulation of a pumping cycle with a dynamic tool. You see in this dynamic tool that we discretized also the tether, and if you look closely you see that the tether is sagging, or sagging a little bit, especially once we go from reel out, which is now, into reel in, which is actually now, then the kite typically sags, because there is a force difference between reel out and reel in. And what I forgot to say, first the kite is not reeled in and it rises up, then we reel in. What happens now? So that's the split of the reel in phase into a constant radius elevation angle increase, and then a reel in at more or less constant elevation angle. We will look into exactly this in the next two lectures with all the math that comes with it, but I wanted to show you a simulation beforehand. That's how the simulation would look if you would plot the entire trajectory. And this, what you see here, is the two stage reel in, or a two-stage phase, where we first have a transition where the kite has not been reeled in, but just once we stop the pulling phase, the reel out phase, we point the kite upwards and it just flies to here without any propulsion. This is simply a process because the kite here is not in an equilibrium position. So it flies to here and then we start reeling in and we have to transition again. This is the simulation of the power curve, but don't mistake this for the power curve. This is an instantaneous power, mechanical power profile. Power curve comes on the right hand side. Instantaneous means here we have time and here we map out the traction power in the tether and traction power, pulling power, simply calculated as P equals force in the tether times velocity of the tether. So this property P we plot here, and you see that here we are about 20 kilowatt in the reel out phase, and in the reel in phase we peak sometimes here shortly with minus 20 kilowatt, but most of the time we're at around 10 or 12 minus. I have now a question for you. Why do you think we see these oscillations here during reel out? What is your idea? Where do they come from? The kite flies during reel out, these maneuvers.
Maybe during the turns, the tether flexes a bit. It slides, right? It slides behind. And since it's not pulling the drum with maximum efficiency when it's slacked, that's how you get those small peaks. Not the large peaks, but the small peaks. Yeah, the valleys. Yeah.
Okay, that is for sure a contributing factor. Other ideas? It is a contributing factor. Yes?
Due to the steering, your lift factor is not perfectly aligned with the tether, and reducing the efficiency of the power generation. So basically, because you're flying values of 8 in the center, you'll have a high peak, while on the turns you're also less aligned with the wind, so that also plays part. It's also turning, so you're generating less.
Yeah, I from what I say is the last point is the most important point, the disalignment of the tether. So in the theory later, you will see that the closer the tether is aligned with the wind vector, the higher the force. This is a core principle of airborne wind. We'll show this mathematically in the next lecture. But just from that concept, you can imagine if the kite flies, tether is sometimes more aligned and sometimes less aligned with the wind vector. And this change in alignment, as you mentioned, that is the underlying core reason why we see these fluctuations. But in addition to that, there is also the additional loss of lift due to steering in the curves, and for sure also the sagging, the stretching and de-stretching. Stretching is not the right word. The straightening and sagging of the tether that you will always see to some degree, especially also here. So, but that's why there are these fluctuations. So this has nothing to do with turbulence in first hand, but it's simply the kinematics of the harvesting process. But then, thanks. So then to get to the power curve, and the power curve of a wind harvesting device is actually not this curve here. This is instantaneous power. The power curve is the power that you can generate for different wind speeds. The power curve is a map of power versus wind speed. And what you see is in this plot we form the integral of the power over time, and that's what you all know as energy. Integrate P over time, you get to energy. And this is the net energy of the cycle. So if you basically equalize, if you accumulate all of this energy in a battery, and that comes out of the battery, and then you calculate the average power, you would get to this line. So of the 20 kilowatt that you harvest here, about 12 kilowatt maintain in average. And the rest is here, the red area, and this one is balancing each other out. It's a bit a simplified picture that I give you because there are also losses. Let's say this energy needs to be converted into electricity, stored in the battery, then taken out of the battery to drive the motor as the generator as a motor here, and to pull in the kite. And in this chain of conversions you have losses, which lead to lesser electrical power than mechanical power. But anyway, so at this wind speed, here was a ground wind speed of 6 meters per second in this, this is actually a simulation. And these 6 meters per second, you find them here. We plot the 10 kilowatt, sorry I have different scales here on that axis and here. So we plot that here. If we now do the simulation or the or measurement for all different ground wind speeds, so every ground wind speed we get a different diagram, then we end up with this curve, and this is what we call the power curve. And you see that this measured 12 kilowatt here in this diagram is about the highest value. That is what we call the rated power at the rated wind speed here of 6 meters per second. Is that clear how I get from instantaneous power to power curve? Maybe what's also important to mention, at least, here I write ground wind speed. Nowadays we don't use the ground wind speed anymore with kite power or airborne wind, but we use the wind speed that is at the altitude of the kite. This ground wind speed simply comes from the fact that we measured the wind speed at the ground, so that was the only value that we had. But nowadays, to be comparable with turbines that measure at hub height, we also go to our hub height, which is the mean flight altitude of the kite. So typically you see here that you see, now I should be careful, when this is wind speed at altitude, you see higher values, because the wind speed at the ground of 6 meters per second at higher altitude is often than 10. So this whole diagram shifts a little bit. We also used airborne wind energy on Mars. Mars has a very thin atmosphere, 1% of the density of Earth. And kites are ideal for powering Mars habitats. We found European Space Agency is also interested in this subject, and yesterday I presented this project here that we did with 2 design synthesis exercise teams and a master thesis here at TU Delft as part of this so-called Rhizome project. Here are Mars rovers, although here on the moon, but it's the same, the lunar zebra, and here's the Habitat 3D printing project. And the idea was to basically go from our on-Earth kite power system to something on Mars. Working principle, I needed to explain this yesterday, and this is actually, these were the challenges, extra challenges here on Mars, and I just bring this up as one option how kite power could be used in the more far down the road future, not tomorrow, certainly not, but let's say all the space projects have already have of course a very long time horizon. That's just something I wanted to quickly mention, and then head over to here, our power curve. Okay, so we move from power curve to the system in more detail. So this is the system of TU Delft. That's the kite. You see here in front view the front bridle line system in black and the rear bridle line system in red. It looks very complicated. Here are the dimensions. It looks very complicated, but I will try to explain exactly how it works. The black lines, they are non-movable, and the red lines are actuatable. Yes?
Question, can we have a look at those Martian slides, or can I?
Yes, I can make them available. I even have the videotape presentation. I will get this to you in some way. Yes, it's a 20-minute, let's say, special interest topic, but I will make it available. So the rear bridle line system is composed of these tapes, 3 tapes that come from the control unit. They then link into this steering line, the red line here, that runs through 2 pulleys and is knotted here to the D-power tape. The way this works, here are the pulleys. That's these points here, just a zoom out. This is the right actuation loop, and now you will ask me, why is left suddenly right? That's simply a convention thing. For the kite flies like this. For the kite, this is the right wingtip. As a pilot from the ground, you see it as the left wingtip, but we needed to make a choice at some point. So we call this the right wingtip from the kite perspective, kite looking into the wind, and then this is the right actuation loop, but just that you know why. And this is the left actuation loop. This is the kite from the side. So you see here the red parts, the rear lines, the front part, black lines with the control unit. The control unit is something I want to explain in more detail, and I brought you the real thing here. This is the 10 kilogram control unit of TU Delft. That was also used by Kite Power. You see here the logo still on there. After 10 years of testing and falling out of the sky several times, a little bit damaged here and there, but it still works. So this is the cover to protect against shock. It was built actually in 2011. We can open here some of these nuts to lift off the cover. So this cover is also made shock resistant, and you see it already got a few hits. It's also watertight, so this control unit can technically fall into the water because we build it also for ship deployment, marine deployment. What you see in the control unit is out. So the other cover left inside here. So you see here the frame. You see 2 strong servo. Sorry, these are the 2 strong servo motors. This here these are planetary gears. The planetary gears bring the very high RPM of these motors down to, let's say, feasible real-out speeds for these tapes. We have here the power tape, so the central tape here with the knot where the steering line runs through, and that is up. You see this. Here you have the drums. We chose for these tapes, so we have a very orderly and nice roll-up on the drums. And the two steering lines here, they operate on the other drum, and the other drum is actually two. They are mechanically linked together so that the steering input only requires a differential force. You can imagine for the deep power tape, you need to pull all times. You see that from this setup, the deep power tape you need to keep at all times under tension, while the steering lines coming in here, running onto the two mechanically linked drums, they only require differential torque to be moved. For the reason that this deep power tape here needs always tension, we built in a brake. The first thing the mechanical engineer thinks of to actually brake the axis, and I'm not sure where this, the brake is here. So this is a small piston that can be actuated against the axis, and that reduces the force when you don't move this tape to very low value. Then next we have a computer in here, the brain of this control unit. We have a wireless antenna here. Here were also two large accumulator, rechargeable battery packs integrated. So you could fly this thing for 2 hours continuously without any onboard power generation. That's of course possible only for testing purposes, because for wind energy harvesting you want continuous, no limits flights. So they built an onboard wind turbine, which I show later. Are there any questions regarding this nice setup? So it's a prototype. It had many features, also a pyrotechnic wire cutter. Yeah, this is the connection to the main turbine. Yes?
How large is the current version? Because
yes,
this is already quite old.
This is quite old. I mean, let's say 15 years is not that old, but in terms of our development, it is old. Current version has stronger motors. The size of this pack is not substantially bigger. What is bigger is the padding has moved from this to this. So the whole thing is now from the tabletop to here and about this size. It's really it has grown substantially in geometrical size. Yes, any other questions? I'll put this back in. And maybe also interesting to know, I think around 15 master theses went to this project here. And of course, not all aerospace engineering, but also product designers work on this. Also all around the world, students who came on a research visit to us. It's a nice, let's say, proof of international collaboration. And it's also the reason why we never patented this in the end, because there were so many people working on this, all this IP was in the end distributed. Yes?
Do you know how much torque those servo motors can
Wow. Now you're asking something that I would need to look up. I don't know this from my head, from the top of my head. But of course the high RPM motors, not a lot, but they run at 10,000 RPM, but then through this gearbox you get quite a strong pull.
Oh, there's a gearbox.
Yes, planetary gearbox. And also these two pulleys, they increase the force by a factor of 2, right?
Yeah.
With the pulley you have twice the actuation length, twice the actuation length, but you increase the force by a factor of 2. We're here. You see with 9 meters from top of canopy to control unit, this is already a sizable installation, but it's shorter than you would think. Kite borders. This kite was, and the whole setup was actually optimized for very short distance to be able to hang it upside down from a mast. So that was one of the design criteria here, to have a short mast, to be able to hang it from the mast. Kite control unit is then at the mast top to launch then from an upside down position. We will see this later. So this is the powered and this is the depowered state. And you see that the wing is now pitched down with respect to the tether. And here you see the whole thing in flight. You see the kite flies in this direction, pitot tube and a badminton bat. And you see that the inflow comes from here. You see here the depower tape, the left and the right steering line. Here the two pulleys. You see the left actuation loop and the right actuation loop. And okay, this is something that I just explained. Maybe I have some values here. So it's shock proof, of course. It has these two micro winches. We have the piston brake that I mentioned, the onboard computer and Wi-Fi antenna. We had the plan to have all the intelligence built into the control unit, so also the steering computer and everything, to be able to have many kites in the air and have them communicate with each other wirelessly and synchronize their flight paths. This is still a bit a future scenario we are aiming at, but it is possible. I mean, the onboard computer is there. And of course, these things here that I mentioned, and encoders, meaning kite power is all about control. For control you need sensors, so every movement of these motors, the brake and other actuators, we logged at high frequency to actually then use it later for evaluation of the data. This is how the bridle line system works, but it's kind of explained also by previous posts, so the front bridle line system and the rear bridle line system. And that's the setup, the control. We call this the KCU bridle because it's actually responsible for the actuation. What you see here is, as a side note, this is the fluid structure interaction model that we implemented last year with a PhD researcher. So instead of going to a finite element discretization of this wing, which you can imagine is quite complicated, we did it once, 10,000 elements you need to resolve such a wing to a sufficient degree. Instead of doing this, we went to a particle system. Each dot here is a mass particle that represents its part of the wing, and these particles are connected with springs, elastic springs and dampers, and we were able to simulate the deformation of this wing as a result of the actuation to quite a high degree of accuracy with such a particle system, all in real-time capability. So that's a research track that we pursue at the moment. And this is for validation. We use the onboard camera of the KCU to actually look at the wing at different instances to validate our simulations. Oh, this is a video. Wait a second. It's quite nice to watch this. If it works, yes. So you see the kite in flight. Power tape, depower tape, steering line. It's here. Front bridle line system. You see here also 2 sensor boxes, or 3 actually. This video is from 2017, when already kite power was operating. As you see how the wing goes through figure of 8 maneuvers, you get a bit drowsy if you watch this all the time. And then at some point, I think it even goes into reel in. I'm not sure. Well, there are parts when nothing changes. That's when the kite flies up during a figure 8, and then in the turning maneuver you see constant rotation of the horizon. That's the background here is Leiden and Falkenberg airfield. Good. Can I have control? That is weird. For some reason it went to the end. Just get the point where I was. Okay. Here you see a launch from the mast. Photos that show the kite in powered state. So when the power tape, depower tape, is fully pulled in by the control unit. So you see that this knot is very close to the control unit. Here you see it depowered, so the wing is pitched down relative to the tether. You can see this from this point. So here I use photographic footage to actually illustrate the different states of the wing. And here, depowered and steering, very extreme case. You will not see this when we fly. I saw this only once when we had the kite hanging upside down on the mast, and the pilot was desperately trying to get the kite launched in a curved maneuver up into the air. And in this hanging position, there is no wind speed acting on the kite, so the forces are very low, so he needed quite a lot of actuation to get the kite doing something. This is the launch maneuver from a bit more distance. You see upside down hanging, and then this actually move into the upright position. This is a detail from the mast launch head, maybe a bit too detailed for here, how you can again use the pulley mechanism to release the main tether, which is this here. And then, then going into the free flight mode. This is the launch maneuver, synchronized from 2 different cameras, onboard to the right and offboard here. And you see how this maneuver works, and then the kite flies off. From many different trials, this was one of the few that actually worked. So that was the real, let's say, difficulty of this launch maneuver, with the very low wind speeds that you have on the ground, to actually fly the kite in this loop maneuver to launch off. Sky Sails solved this differently. They put the kite in the normal configuration and then just use static wind to slowly lift off. That is possible with a soft wing. That's the ground station. So you see here the drum and the generator, and this is a belt drive to connect them. The tether comes from the drum, goes through 2 pulleys into the swivel head. The function of the swivel head is to be able to rotate with the wind. And you see this illustrated here. So that's the drum, which is inside here, and 2 pulleys with the swivel head here. And this red dot here is a load cell that we use to measure the tether force. As I mentioned, it's everything about measuring in our phase be able to use this data then later for simulation validation. Okay, then we move over to kite power, and that's a smooth transition because they basically in 2016, it's 15, end of 15, they got all our hardware. I mentioned it earlier. as a research group, it was very difficult to maintain such a system and operate it. So we decided to spin off a company. We also got the funding for that, and we registered our spin-off. But the rest of the system stayed the same. The mission of the company was now to actually earn money. That was not our primary mission earlier, so they really needed to also to go to market. They perfectionated their automatic flight control, I would say. You see how precise the tracking of the flight path is here, figure-8 maneuvers. And this is the return trajectory with the two transition phases here and here. And this is how it looked like when we were testing in Falkenberg. I think 2018-19, you already had drones. It's from the same time. And testing got more and more professional. So we needed to also develop safety procedures. When we started in 2013, it was just a bunch of people going with the setup to Falkenberg and launching the kite there. 5, 6, 7 years later with the company, there was a launch protocol, there was a concept of operations that needed to be followed. People needed to be trained on their specific components. So this is already the 100 kilowatt ground station. It fits the shape of a 20-foot ship container. You see here 3 kites already in launch configuration. And this is basically the operational zone concept with the different distances from the system that you need to maintain, and a safety zone and a dual use zone here where you could have, for example, agriculture, rural use of the land, or then completely, let's say, secured off area. At that time, we also looked at kite park layouts. So we have a book chapter about that, and how you could, maybe that is why it's interesting, if you have multiple systems, you can operate them in phase-shifted pumping cycles. And if you electrically connect these systems, you don't actually need a battery anymore. You need a small battery to launch the first system, but the more systems you add, you can lift the entire production profile into the positive. We showed this already with simulations. The blue system is 1 kite, and you see here is 0 power, and you have a real out phase, real in phase and real out. You see that it goes around 0 with 16 kites. You can already bring everything up to positive power. So all the electricity fluxes in your 4x4 matrix bring the net produced power, or the instantaneous power in the electrical network to plus, and with 8x8 kites even more. Yep.
What does it mean when the power is negative?
Like here.
Yeah, or the red one.
The red one. That is a transient startup phase, and I'm not sure how we actually did that in these simulations. For this we used a dynamic simulation tool, and I believe that this is simply a startup phase that was required to synchronize the phase shifted operation and bring that. I know that we used an optimizer to drive that process, but that optimizer had a certain startup time. But I mean, it's a very detailed question, yes. But the important thing is that after the startup time, basically level out here. And this is about, I think, 1.5 megawatt with 64 kites. These are all, I think, 100 kilowatt kites. So that's the ground station. I need to rush through the 100 kilowatt ground station built by Dromek, a winch manufacturer here in Holland. This was a very expensive ground station. You see it could rotate here with the wind, with a large gear, 360 degree. It had a very nice cable guidance mechanism and so on. It was built for test purposes. Here you recognize the onboard wind turbine, the first prototype. It is hooked up to the control unit and it generates the power during flight. You see it here. This shroud is not a shroud for aerodynamic purposes, but for safety purposes when the whole control unit lands. At that time, we still needed people on the ground to hold the kite and catch it, and so we needed to provide some mechanical protection because the wind turbine blade can spin rapidly. Yeah, here you see nicely the size of the control unit, and you can already imagine that this is quite bigger than this little thing. The kite is also 60 square meter here already, so that's the V9 kite, and here we are in Zeeland. Then 2021 we went to Aruba, so the company had a contract with the Dutch military to provide the power during a training on the island, which lasted for 3 weeks. And as part of this was the shipment, the deployment, and the operation of the system on the island, actually next to a wind park. 2023, we charged electric cars in Zeeland, which is a nice demonstration, of course, what that system could be built for. Off-grid distributed power. It's also one of the business cases the company looks into, and that power can be for car charging, but also for construction sites or other purposes. Then this is 23 in Ireland. I mentioned earlier County Mayo, the new test site where they now operate several flights per week, if not per day. These are all test flights now to get the system to market-ready status. Let's see if I can continue. Yeah, then we have a few slides on Kite Energy. It's an Italian startup. It's very similar. Sorry, it's from 2010. It was one of the early companies. They use a ram air wing, and they had multiple winches on the ground to steer the kite. And here's one photo from a few years ago. You see the ram air wing in nice Italian colors. See here multiple tethers coming down to the ground station from where it was steered. Then we have Toyota. Toyota is involved for a few years. Toyota Motor Corporation. They have a project that is called Mothership Earth, and as part of this they want to push airborne wind as a new renewable energy technology. They operate in Japan and also in the US. They have two centers where they develop airborne wind. They use an inflatable, leading-edge inflatable kite with aerodynamic control surfaces. And that is their last prototype. Yes?
Are the control surfaces powered by battery or also a little turbine?
As far that requires some guessing from my side. I have never seen a turbine on board, but they are also not. They started relatively late, so they are in the phase where they are still testing. So I believe they have batteries right now, or even a power cable to the kite. But the control surfaces are some were built in here. You see that they have this double tube. to get better aerodynamics. So there are still changes that occur. In this book that I distributed, there are more photos of this Toyota prototype. This is already version 11, so they go very systematically ahead with their research. Then we have Enerkite. Enerkite is also one of the early companies from Berlin, spin-off of TU Berlin, also pumping cycle. They started with a soft wing and then transitioned towards a hybrid wing, and they used 3 tethers to steer this wing from the ground. And their speciality is a rotational mast-based launch setup, which you see here. So this is their, let's say, movable ground station, an old fire truck. On the back mounted 3 drums. You see here the 2 steering drums, left and right, and behind that, hidden, is the other big drum for the power line. This is the rotational mast, and here you see the wing linked to the mast, and you see here the 2 steering line coming in. And this should be a video showing how the wing works. This is from last year. So you see how the rotation launch works. There is a more up-to-date video which I couldn't fetch yet, where they also fly off. Okay, they do this here already. So this is the critical phase. You can imagine a swept wing for the flight dynamics people, you know, is anyway a delicate issue without a tail, and to have that decoupling from such a launch mast is even more daring, and to then safely recouple it. So this was quite a success. You see how the wing is actually dragged behind the masthead. It's like a rotational towing setup. But the idea is to then go from this, let's say, axisymmetric launch operation into a downwind operation where the mass is not rotated anymore. That one I have not seen yet. Then Ampix Power. Ampix Power is the second Dutch company on airborne wind. They closed shop in 2022, so very recently. They were, after Ampix Power, the second largest airborne wind company, going for fixed wing, but they resurfaced shortly after bankruptcy under a different name, Mosaero, and kept also some hardware and key development in-house. I will have some photos about that. But let me quickly go through the history. So they started with this tethered aircraft, AP1, then went to the AP2, which had all components of the later AP3 already integrated, but was just smaller. So you see here, for example, these 2 propellers that could be used to give additional boost during launching. You see that here from the bottom, and here from the ground station. So here you see substantial sag of the tether. The propellers of this let's say thrust this subsystem could be folded back to not create drag when in power generation mode. So let's look into the avionics compartment. What you see here, a small detail, this is the onboard wind turbine that they use like we do to get the power for the aircraft when flying. Then they went to AP3, here a cap drawing. This is already a huge aircraft, 7-meter wingspan. Investment also went up substantially. You see the main tether here attaching to the wing center. the aircraft had, of course, many components, and Ampix is known for maintaining very strict aviation quality, redundancy of components of all sorts. They knew that if something breaks or fails, they must have a fallback solution that they can immediately activate. Here you see the two prototypes in their workshop a year before they went bankrupt. And here the vision then for later with AP4 and the whole wind park of these megawatt scale systems floating offshore. I will not go into this. But then they transitioned into Mosa Aero, keeping the same layout. And they actually operate now out of Breda International Airport. They have a hangar and offices there. And from Breda we also have these nice photos. You see here a pitot tube, or two actually. These are launch assist propellers. So what you saw small on the AP2 has become quite bigger here. It looks bigger than 7 meters, but okay, anyway. Here in Breda. Special about this AP3, I should mention it, is this landing gear. You remember from the concept sketch in the beginning, they need to land this on a small platform. And the idea was offshore operation. So on an offshore floating platform that moves while you land through a turbulent wind field, they already realized early to make such a precision touchdown requires a very good shock damping mechanism in this landing gear. So this was a core development, to have a landing gear that could capture and dampen this impact shock. One of my master students actually did the dynamic simulation of this landing maneuver in 2017. Then we move on to November last year. They flew the AP3 in Groningen, no, Ostwold Airport, which is in Friesland. They flew it in an untethered configuration, which was a big success. So you see here some pictures from this test flight. Okay, this is a movie. And the plan now is to, they just gotten into a project funded by the Belgian government for test flights in tethered configuration. So we will see news about this at some point. Then I have slides about Makani, but I think we have to skip those. I wanted to, because Makani stopped operation in 2020. I will move over this because this is not core essential now. What's probably better is here to move on to Kitecraft, which is launched in the shoes of Makani with onboard generation. So here, spin-off of TU Munich, and they have a tail-sitter VTOL drone, which is here depicted. That's the 100 kilowatt system, as far as I know, and they use multi-element airfoils for increased lift. Here is the test in the wind tunnel of TU Munich. I think it's TU Munich, I'm not sure. And here you see a test flight. Yeah, okay, here we go. So that's not the 100 kilowatt system, that's the smaller scale, I think 10 or 20 kilowatt system. You see now why it's called tail sitter. So here they just hover off. Electricity comes through the tether, and then they go into crosswind flight. Transition again between liftoff and crosswind is critical, and also from crosswind back to landing. Then we have TwingTech, TwingTech Swiss spin-off from EMPA. They use control surfaces and pumping cycle. They have this very nice photo here of their wind energy system compared to a turbine, both of the same power output, which I think is pretty impressive illustration. So you see the massive material use that you can achieve. And this is a video how they operate. So you see the three VTOL systems, the onboard turbine you saw, and also that the wing flies a lot faster than a soft guide. That's their gear drive. And then with this we can end. Kite Mill. Kite Mill is in Norway. Is also quite old. They started with soft wing and then went into fixed wing, and they have a similar system as TwinTech does. They are also, let me mention this, very open for internships and graduation projects. They have recently won an EIC accelerator grant, which starts now with I think 2.5 million, and can in later phases go up to 10 and more million. So they are on a good track now to also be in a leading position. And I can only say many of my students from Delft ended up in Lista, where they are based in their team, either working on aerodynamics or on control or on other topics as interns, and some of them already also continued later on as employees. So they have a large inflow from this faculty here in terms of employees. And that holds also for the other companies, I should say. So if you are interested to join one of these initiatives, either as an intern or for a graduation project, just contact me and I bring you in contact with them. So they all need talented engineers, and they are very happy that we are one of the institutions that can already, let's say, prepare students with airborne wind energy knowledge. I think with this we can close for today. That was now the third lecture. In the next lecture we will look into the theory of tethered flight, and then the colorful pictures stop, and we move to vectors and scalar equations, very interesting ones. We will use at some point also spherical coordinates to develop theories how you can describe this mathematically. Thank you, and see you next Friday.